Welcome to aminacademy.com. In electrical engineering, let us discuss about work, power and energy. Today, human life without electricity is highly unimaginable. Without electricity, we can't do anything. Electric locomotives, heaters and fans and lightnings are some of the appliances of machines which converts electricity into work and energy. It is a matter of common experience that a conductor, that is electric conductor, when carrying current, become hot after some time. As explained earlier, an electric current is just a directional flow or drift of electrons through a substance. The moving electrons, as they pass through the molecules of atoms of that substance, collide with each other electrons. This electronic collision results in the production of heat. Now, we know that electric current is the result of flow of electrons. The work done in moving the electron stream is known as electrical energy. That means energy required to move the electrons. Electrical energy can be converted into other forms of energy such as heat energy, light energy, etc. For example, in an iron box, electric energy is converted into heat energy. Likewise, the electric energy in a bulb is converted into light and heat energy. There are two types of electric current known: alternating current, that is AC, and direct current, DC. The direct current can flow only in one direction, whereas the alternating direction current flows in two directions. Direct current is seldom used as a primary energy source in industries. That is, AC current is useful in industries. It is mostly used in low voltage applications such as charging batteries, aircraft applications, etc. Alternating current is used to operate appliances for both household and industrial and commercial use. The electric current is measured in ampere. 1 ampere of current represents 1 coulomb of electric charge moving past a specific point in 1 second. According to Joule's law of electric heating, the amount of heat generated is proportional to the resistance of the wire, the time duration for which the current flows, and the square of the current flows through the current circuit. Now, Joule's first law. The Joule's first law shows that relationship between heat produced by flowing electric current through a conductor. That means here Q equal I squared R RT. That is Q equal where Q indicates the amount of heat, I shows electric current, R is the amount of electric resistance in the conductor, T denotes time. The amount of generated heat is proportional to the wire's electrical resistance. That means when electric resistance is more, heat produced is more, when the current in the circuit and the flow of current is not changed. The amount of generated heat in a conductor carrying current is proportional to the square of the current flows through the circuit when the electrical resistance and current supply is constant. The amount of heat produced because of the current flow is proportional to the time of flow when the resistance and current flow is kept constant. That means the amount of heat is proportional to the factors of current, resistance and time. Now let us do an example problem. Here, calculate the heat energy produced in resistance of 8 ohm when 3 ampere current flows through it for 4 minutes. Look at here. Here heat energy H equal We know the formula I square R T equal I is current 3 ampere, that is 3 square, resistance is 8 ohm, and time 4 minutes is 4 into 60 seconds. Time should be in seconds. So which gives 17280 joules. Converting kilojoules, it is equal 17.280 kilojoule. Here we'll do what is thermal efficiency. Here it is defined as the ratio of the heat actually utilized to the total heat produced. Therefore, thermal efficiency equal is the ratio of actually utilized heat, over total heat produced. Total heat produced by electrically. Now, which is equal, therefore thermal efficiency is equal VIT over J joules. Therefore, efficiency equal MS into theta 2 minus theta 1 over into joule over VIT. Here, mass of the substance, S is a specific heat, and theta 1 is temperature differences, and V is volts, I is current, and T is time in seconds. Now let us do an example problem. The heating element of an electric kettle has a constant resistance of 120 ohms, and the applied voltage is 240 volts. Calculate the time taken to raise the temperature of 2 liters of water from 20 degrees Celsius to 90 degrees Celsius, assuming that 85% of the power input to the kettle is usefully employed. If the water equivalent of the kettle is 100 gram, find how long will it take to raise the second liter of water through the same temperature range immediately after the first. Now let us write the given things first. Here resistance R is given. R is 120 ohms. Voltage, supplied voltage is 240 volts, and mass equal, mass of water is 2 liter, which means 2 kg, and heat taken by water heat taken by water is, that is M theta 2 minus theta 1, which is equal, mass is 2 and degrees T1 and T2. Theta 2 we can write 90 degrees Celsius and theta 1 equal to 20 degrees Celsius. Now here that is heat energy is mass is 2 into 90 minus 20, which is equal 140 kilocalories. Now by kettle, heat taken by kettle is heat equivalent is 100 gram. Heat equivalent of kettle is 100 gram, that is 0.1 kg into same temperature difference 90 minus 20, which is equal 7 kilocalories. Now total heat taken is 140 plus 7 equal to 147 kilocalories. Since water should be heated as well as the kettle should be heated first. Therefore, heat produced by electricity, it is heat taken by water, heat produced by electricity. Heat produced by electricity is H equal to I squared R T. Now, I is V by I, voltage by current. Voltage is 240. Then resistance is 120 square into R is 120 and time we need. Time taken we need divided by joule in kilocalories. Now equating this both, this total heat taken by the water, total heat produced by electricity. So we have to equate, because the efficiency is 85%, that is 0.85. 0.85 into 4. 4 is 0.85 into here 0.85 into here 2. This is equal to 2 square is 4 here, that is here this R square, I squared is 4 and R is 120. Time taken by 4500 equal 147. That means that efficiency into heat produced by electricity is equal to heat taken by water. So we are equating from this time taken. Therefore, by cross multiplying, we will get time taken is 147 into 4500 over 0.85 into 4, that is 4, that is I squared into 120, which gives 1621.33 2.3 seconds, converting minutes, which gives 27 minutes and 1.3 seconds approximate. So this much time to take to raise the temperature from 20 degree to 90 degree of 2 liter of water. Now in second case, look at this second case here. Find how long will it take to raise a second liter of water through the same temperature range immediately after the first. That means here same that 140 means heat taken by water itself. Here we are not considering kettle because kettle is already hot. Kettle is already hot. So we are taking 140 only the water heat required to heat the water is equal 140 equal. The efficiency is 0.85 into 2.5 square, not 2.5 square, that is 2 square here. That's good. R is 120 or the time T over 4200 into T. Therefore, from this T equal to 140 into 4200 divided by 0.85 into 4 into 120. Let us calculate this. Here 140 into 4200 divide 0.85 into 4 into 120. We call 1441 seconds. 1441 seconds, which approximately equal divided by 60 gives 24 minutes 24 minutes and 1 seconds. This much time take. So far we have done. Please subscribe our YouTube channel.